Right, so here is the second required practical on waves. Okay, so here we've got something called a standing wave. So what we've got is a string attached to a vibrator, and then we've got it attached to some weights using a pulley. This is just to give the string some tension, and the signal generator controls how many times a second that goes up and down. So the frequency here, we've got a frequency of 50 hertz, which means the vibrator will go up and down 50 times a second. So a standing wave is basically when it appears that the wave is stationary. So what we end up having is these things called nodes where they don't move just here. Okay, and that allows us to measure the wavelength. So let's get started. So here we've actually only got half a wavelength. So each arrow marks the start of half a wavelength, and the next one marks the end of the half wavelength. So in this case, we've got 1/2 wavelength, and the distance of half a wavelength is 200 centimeters or 2 meters. So because we've only got 1/2 wavelength, we say there's 1/2 wavelength, and the distance of the half wavelength is 200 centimeters from there to there. So that means the distance of a full wavelength, 2 halves, so 2 lots of 2 meters, is 4 meters. And then if we know the wavelength and we know the frequency, of 10 hertz, what we can do is work out the wave speed, 10 hertz, which we get from the signal generator, and we know that the wave length is 4 meters, so it's 40 meters per second. Now let's look at the next one. Here you can see we've got the full wave there now, so it goes down and then it goes up. So here our total distance of the wave is still 2 meters, 200 centimeters. The number of half wavelengths is 2. That's 1/2 wavelength, that's 2 half wavelengths. And the distance of a half wavelength is 100 centimeters or 1 meter. The distance of a full wavelength must be 2 meters. So we've got a wavelength of 2 meters, and then we've got a frequency of 20 hertz. So we do 20 times 2 gives us 40 meters per second again. Now, exactly the same again. The total wave distance from there to there is 2 meters. The number of half wavelengths this time, looking at this, is it goes down and it goes up and then it goes down again. So we've got 3 half wavelengths. So the distance of a half wavelength is actually 67 here. Okay, so 67 or 0.67 meters. The distance of a full wavelength is 2 lots of that because it's from there to there. Half and half makes a whole wavelength. So 2 times 0.67 gives us 1.33 meters. So all we do now is do to work out speed, frequency times wavelength. So 30 times 1.33 gives us 40 if we round it. Right, the next one. Total wave distance here is still 2 meters. The number of half wavelengths this time is 1, 2, 3, 4 because it goes down, then up, down, then up. So then we can say there's 4 half wavelengths. The distance of each half wavelength is from there to there, which is 50, 50, 50, 50. So 50 centimeters is 0.5 meters. And the distance of a full wavelength, because it's 2 lots of 0.5, is 1 meter. Okay, so then we just do frequency times wavelength. So 40 times 1 gives us 40 meters per second. Okay, and it's the same as before. I'm not going to go through this. I'm just going to put the answers on there like that. You can pause the video just to double check that's correct. But as you can see, the speed remains constant like before. So let's have a quick look at a past exam question that could be asked. The following figure shows the apparatus used to investigate the waves in a stretched string. Okay, it's put under tension by the masses, and we've got the signal generator and a vibrator going up and down. It's creating a standing wave, as we can see there. Okay, the frequency of the signal generator is adjusted so the wave shown in the figure is seen. At this frequency, the string vibrates between the 2 positions shown in the figure. The wavelength for the shown in the figure above was measured as 80 centimeters. So you can see it. One wave, because it goes up, then down. The half wavelength is from that point to that point. So we've got two half wavelengths to make a single wavelength. What piece of apparatus would have been suitable for measuring this wavelength? As we said, we use a ruler, not a meter stick, a ruler, which is what we did in our examples. We get this equation from our equation sheet, and then all we do is work that out. So we get our wavelength from here, which is 0.8 meters, because we always measure it as meters, and we times it by the frequency of 55, which we've got from the signal generator. So we've got that, and that gives us our wave speed. Right. The frequency of the signal generator is increased. This makes the wavelength of the wave change. The wave speed stays the same. Describe how the apparatus could be adjusted to show one complete wave without reducing the frequency. So if the frequency was increased, you would have more waves within that gap of 80 centimeters. So rather than having one single wave, you might have two single waves. So what would you have to do? What you would have to do to get a single wave is close that gap and move the wooden bridge closer so that two waves become one again. So move the bridge to the right. Okay. You could add more mass, but it's easier to work out that. So a student wants to investigate how the speed of a wave on a stretched string depends on the tension in the string. The student uses the apparatus in the figure above. Describe a method that could do that. So to adjust the tension, all we have to do is add more weights, and that puts, or more masses, sorry, and that will put more tension on the string. So if we add or take away masses from the string, okay, that would either increase or decrease the tension. Okay, so let's add some masses to increase the tension. What we would then do is adjust the frequency using the signal generator, okay, until we get a standing wave or stationary wave. Stationary so we can then measure it. We would then calculate the wave speed from the frequency and the wavelength. So what we could do is get the frequency from the signal generator, and because we've got a wave that appears stationary, we can then work out the wavelength or measure the wavelength using a ruler, and then times the wavelength by the frequency. The key thing to remember here is we can adjust the tension by adding more masses